Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This work isn't actually my work. It was done by Susanna Avila-Garcia, but unfortunately she decided to go get married instead of coming to present it, so you've got me instead. But I would ask you to have patience with me on where I'm not entirely flush with everything. I'll try and answer any questions you have, but yeah. Okay, so a quick outline of what we're going to talk about. And first I'm going to look at colorectal cancer and why this is a significant issue. I'm then going to look at some of the work that's being done in Oxford to address this problem. After that I'll talk about the various bits of the project before looking at the challenges that we expect to face and are facing, and our future work and conclusions. So starting off, colorectal cancer is diagnosed in about 36,000 people every year in the UK, making it the third most common cancer. To make it worse, though, it quite regularly spreads to the liver, and this results in an additional 3,000 deaths every year. It's normally detected through a range of scanning techniques, such as CT, ultrasound, MRI, and once it's been detected, you then monitor it. They continue to monitor it like that and decide whether to do surgery or whether to radiotherapy or the various other options that are available for dealing with it. So once you've got these images, though, there's a lot of work done on the analysis of them. So in Oxford, we're looking at various different algorithms to assist in this because, for instance, you want to segment the image so that you can tell what the different bits are. So you'd want to, for instance, draw a line around the bladder here as the colorectal, and you've got the hip bones out on either side. But the problem with doing this is it's fine to do it for a single image, but normally you're looking at sets of images where you want to go around all of the different parts of the image and calculate the volume of the cancer and see whether it's growing. We also want to do image registration because it's all very well being able to segment the image up into the different pieces, but if you take a set of images of you now and another set of images in 6 months' time, most things like your skeleton and such like will stay put, but your bladder will move according to how much liquid's in it at any given moment, and you need to be able to get all this line up. And again, once you're dealing with large sets of images, there are better things to pay highly qualified surgeons to do than going through and going, well, those two match up, those two match up. So there's a lot of work going on automated and semi-automated algorithms. For instance, you say in one image, that's the bladder and matching onto this bladder, and then it goes to the other images, being able to work out and automatically segment them, and you put points around the side saying this is the line where we want to draw lines around. And also there's the improvement of the image quality because images tend to be quite noisy, very highly textured, and also you end up with a fairly poor contrast to the surroundings in the raw images, and so you're always looking to see how you can improve the quality of that. And so there's a lot of research in Oxford going towards how to do these different and better algorithms and improve these images. So with the aim of helping out on this, Microsoft, two of the projects that are currently funded by Microsoft, though I'm well aware that there are many others, include the top one, which is developing new segmentation algorithms to do automatic segmentation. And then the one I'm going to talk about today, where what we're actually looking at is how to make it easier to take advantage of the research that's going on, both for the clinicians and for other medical researchers. So at the moment, people tend to work on their own. They publish papers occasionally, but it takes a long time for things to come around. And once the information's come around, it takes a lot of getting hold of the raw data and the algorithms, then pulling all the papers and the documentation together so that you can get it all to work is quite challenging. So we're looking at how to do that, and also looking at how to make it easier to do things like inserting the human element to the semi-automatic algorithms. But I'm going to talk about that later on. Okay. So in order to make it simpler to handle all of this, we've designed a framework which we're looking to implement that will allow the researchers to share both the data and the algorithms that they've stored. It'll bring in all the papers. So I'm just this off it. and the visualization tool, so that everything, basically pulling everything together into one place and making it universally shareable, both within the university, across the country, and ideally across the world. But the intention is to build this on top of a cloud computing framework, so that it can scale up nice. We don't have to decide how big a cluster we want to build in the first place. We can, as and when we want to expand it, you can just buy more space on whoever's cluster or cloud framework we're using. We also are looking at how to make it easier to put in the information, and although I'm not going to talk about that today, if you want to come and see about the work that we're doing on that, there's a talk on it on Wednesday where we'll talk about the various experiments we've done with alternative ways of inputting data. So the aim is, like I say, to build on top of existing cloud work. So because we don't want to have to write everything out from scratch and reproduce stuff that lots of other people have produced before. So we want to take, where possible, the work that's already exists in cloud computing and then just layer on top the extra bits that we require. So for instance, we hope to be able to get things like the setup for publishing the web services to access this framework directly from a cloud computing framework. We would expect to be able to get some of the security features that we'll need in order to control access to the data from such a framework, and the ability to store certain amounts of metadata. We'd also, though, expect not to be able to get all the metadata storage and the provenance storage that we would want to go with this. We may not be able to get all of the security information and the interactions with the various toolkits. So what we're hoping to do is layer a cloud on top of a cloud effectively. So if we look at the structure of what it is we're planning to layer on top of there. So at the moment, the researchers are using a sort of a jumble of different languages, different experimental data sets, and they publish all their results and they go out on the web. So we'd like to be able to draw all this together and then connect it to the various toolkits that they're already using, so as to make it easier to tie together all the image analysis and put it all in one place, so it's easier to gain access to. You can just install it from a client running on whatever system, and it comes across as a rich application on the web, either as a thin client or just through a browser. Having done that, we would like to layer something like Microsoft Workflow over the top of that to provide a means of tying together these different toolkits and transferring bits of work between them. That also raises the potential of researchers publishing the workflows that they've got to tie together existing algorithms, and then these being, you can then start building this up as a hierarchy of workflows to get to the final solutions that you're looking for. And we then want to make that all accessible through a layer of metadata and a set of web services so that you can run it either through web-based applications, so a virtual research environment, something like that. One of the scientific workbenches, many of them of which are available, so you run the workbench on your computer, but the actual jobs would get sent off over the web services to run in a cloud somewhere, accessing data that's again stored out in the cloud. Or finally through an enriched desktop application. And all of this is to enable the medical research the medical image analysis people to make better use of the resources that are available and spend more of their time doing the research rather than trying to piece together bits and pieces of information from papers and websites and emailing around because somebody managed to leave out a file which was important for running the algorithm, but they didn't realize they'd got it on their desktop. So specific applications that we're looking and projects that we're looking to work with for this. There's for the virtual environment and the web-based stuff. There's the work that's been done with my experiment, with Carmen and with the Research Information Centre. For the scientific workflows and workbenches, there's Treverna, there's a Microsoft Workflow Foundation, and there are many others out there, but those are the two that we're focusing on at the moment. And then for the enriched applications, there's things like SkiRun, which enables you to do very impressive and high-quality visualizations of the work that you're looking at. Now, obviously, you don't want to be able to sending all of that over the net, so you would want to send the data to the enriched application and then let it calculate the visualization locally. And then there's things like MATLAB, which they seem very keen to hang on to MATLAB. They like it a lot. But yeah, I mean, we may end up seeing R or something like that turning up there at some point in the future, but for the time being at least, not that. So to do this, we're using among the tools we're using the following Microsoft tools. So Visual Studio is currently used for a lot of the C++ programming which the medical researchers use, and this would make it very easy to attach onto the web services that we propose to make available and to wrap up them. The .NET platform also is very useful because it allows, they've been writing their code in a range of different languages, and it allows us to join those together without having lots and lots of complications about how to run different pieces of code and having to go down to the file system or streaming across through sockets between code. It just simplifies the interaction of the different pieces. And we also want to collaborate with the existing virtual research environment project, the Research Information Centre. So the major challenges that are facing us with this project, to build on the work that people have done so far, is how to adapt things like the existing research environments, the various imaging toolkits, which I was given a long list of names and all of them have escaped me at the moment, I apologise, and algorithms developed by researchers so that they can all be embedded within this framework. How to link to the more permanent repositories so that we don't end up setting up an entirely separate system again, because there's enough repositories, etc., out there already. But we don't want to go and set up a new one. What we want to do is make a single point where you can interact with all these different resources that are out there, because certainly Oxford has a policy that everything we publish has to go into the Oxford repository. I suspect that's true of most universities. And so we want to have a method so that these repositories, which are based on institutions, can be tied together to be based on communities. We also want to engage with the users, because a lot of the medical image analysis people get very excited once you start to show them what could be done, but they're entirely unaware of the existence of these possibilities. And so we want to engage with them, but we also want to engage with the students and the computer scientists, because a lot of them aren't aware of this as an area where research is a possibility, and so the problem remains unaddressed through ignorance rather than it being too boring or too trivial or whatever to be deemed worth their while. So we want to encourage there to be an interaction between these two communities so that people can talk about what is possible and what people might achieve, and also encourage people to go and have a look at the problems. So for the future work, as I said, we need to examine the existing software and work out how we can wrap that and how we can tie all of that together and tie it into our framework. If we're going to do that, we need to come up with a set of designs for, having evaluated the work, we need to come up with a set of designs for how we can pass and store this data. We won't always obviously be able to turn it into a single format, but if we have a set of formats at least, then we know what translators we need to produce and how we need to be able to transfer the data across. The designer, how to implement the different workflow engines. So they've got their different engines, and you can put them on the cloud. But we need to work out how exactly we're going to bind that into the project, and then layer that on top of the image toolkits, etc. And then as I say, incorporate that with the existing image toolkits. And finally, link to the permanent repositories. So to conclude, and I feel I've probably rushed through this far too quickly, they've presented the outline for this framework, and I've detailed where we propose to go with it next and the future work that we need to do in order to turn this from a dream into something approaching a reality. Hopefully entirely approaching a reality, in fact, but we'll see how far we manage to go down this list. And finally, I guess I should thank the people whose work this actually is, and I'll attempt to answer any questions that you have.
Great, so we will take some questions, and again, wait for microphone. And well, I see you pondering what your next question is going to be. I'll start us off. We hear a lot of people talking about cloud over these last couple of days. We don't hear as many people talking about client, and if we think about chipsets and the development of chipsets, the power of the chipset is going to be both in the cloud and in the client. And so a hypothetical question, if you had 100 times more computing power tomorrow, what would you do with it?
I would dramatically increase the resolution of the images we're working with, because often the images that actually come out of the machines get downsized in order to be realistically analysable. And that's something I probably should have mentioned, is one of the hopes with the cloud framework is that we'll then have that extra resources available. So if the clinician's looking at something and decides that the resolution isn't high enough for them, because often they can make the decision without having to look at it in extreme detail, but if they look at something and they're like, well, I want to have a higher resolution of that, they can just hit the button and you'll be able to get the higher resolution. And ideally with more computing power, then I'd want a much higher resolution. Of course, with more computing power, the CT scanners and such like will be able to do much better analysis of the raw data that they're recording, and so you'll get a higher resolution there. So it's an arms race between the two, but definitely higher resolution would be my call.
Question over here.
Questions also relate to this kind of thing. You're basically using this cloud computing, web services based cloud computing. How big is the data site you're talking about? MRI image can be very big, so this I/O can always be a big problem. So how can you handle these kind of things with using cloud computing?
I mean, the hope is that most of the data, once it's gone across onto the cloud, can stay there, and all you'll be sending back is the bit that you actually are looking at any given time. In the same way as the one of the talks earlier on, though I don't know whether you're in that session, was talking about how they visualize in terabyte astronomical data looking at black matter, and doing a very similar technique to Microsoft or Google Maps, where you calculate the little bits that you want to send over, and because the screen size remains constant, and you've got this huge data set behind it, but you actually end up saturating the screen, and so you only need to go to the resolution that the screen's working at, not the resolution that the data set is originally stored at, and then just because once you zoom in, you can crop away all the stuff around the side, and you still end up with a much smaller data set that is feasible to move around. Of course, as screen sizes improve again, you have to sort of hope that network is going to keep up to an extent, but we'll see where things go.
Any last questions? Well, thank you so much. We appreciate it. Round of applause.